Welcome, everyone, to the New Jersey Climate Change Resource Center Special Climate Academy event, focusing on our recently released report, The State of the Climate, New Jersey 2021. I'm Marjorie Kaplan. I'm the co-director of the New Jersey Climate Change Resource Center and the associate director of Rutgers Climate Institute. And it's my pleasure to be here and welcome you all. And I'll be the moderator for today's event. A few logistics: we will be lasting till 1 o'clock. And other than today's presenters and our Rutgers team, you're all muted. So to communicate with us, please type your questions into the chat box, and you'll find that by looking at the bottom of the screen. You'll see the little chat bubble. I'm sure you're all familiar with it by now. And you can send us questions and comments. So please send your notes to panelists, as that ensures all of us working behind the scenes today will see your questions. I want to thank my colleague, Matt Drews, here at Rutgers for his help with today's webinar. I also want to let you know we are recording today's webinar, and it will be available on the New Jersey Climate Change Resource Center website, which I will type into the chat box right now. And today we're very pleased to have wonderful speakers. We have Dr. James Shope from the Climate Change Resource Center in the Department of Environmental Sciences. And we have an all-star lineup. In addition to James, we have Dr. Anthony Broccoli from the Rutgers Climate Institute and distinguished professor in the Department of Environmental Sciences here at Rutgers, and Dr. David Robinson, the New Jersey State Climatologist and distinguished professor in the Department of Geography. In the interest of time, I don't need to go over their bios, but we encourage you to check them out on our website. And again, I'd like to remind everyone to put your questions in the chat box and send them to panelists. And with that, I'd like to invite James Shope to kick us off. So take it away, James.
All right, thank you very much, Marjorie. Matt, I am going to share my screen now. And give me 1 second to get everything going. Okay. All right, well, thanks, Marjorie. So today we're going to be discussing State of the Climate, New Jersey 2021. This accompanies a report that we recently released at the end of April from the New Jersey Climate Change Resource Center, Climate Alliance, and Rutgers University in general. And to give you a sense, this is the front page of the accompanying report. You can see all of the author list. And let me get the little laser pointer here. The author list, as well as our various affiliations. And you can see that this report was a good cross-section of Rutgers climate and research folks. All right, so let's start the entire presentation with just an overview of climate change. So climate change is driven primarily by greenhouse gases, primarily carbon dioxide. So the combustion of fossil fuels, so we're talking coal, petroleum, natural gas, emits carbon dioxide into the atmosphere. And we're currently emitting somewhere in the ballpark of 10 billion tons of carbon dioxide per year, or carbon per year. This graphic here is from NOAA, and it shows measured concentrations of atmospheric carbon dioxide at Mauna Loa in Hawaii. So it's in parts per million, as you can see on the y-axis. And since we've started measurements in the 50s, our carbon dioxide levels have just increased over time at an accelerating rate. You can see this curve here in black is trending upwards and has a curve to it indicating that it's accelerating. And we're currently consistently above 415 parts per million, which, you know, back in the 1950s would have been unheard of. Now, carbon dioxide is our greatest contributor to global climate change, but it's not the only greenhouse gas. We have a whole bunch of others, but carbon dioxide is our largest driver. So this is an image from NOAA. It shows radiative forcing, if you want to think of that as just proportion of climate change that a particular greenhouse gas is responsible for. That'd be an easier way to interpret this. And if we look at 2020 here, just at the end of this graph, you can see that the largest proportion of that climate change responsibility goes to carbon dioxide, followed by methane here in the green, and then a smattering of nitrous oxide, chlorofluorocarbons, and halocarbons. So carbon dioxide is about 66% of the observed warming, with methane about 16%. And those increasing greenhouse gas concentrations result in warming or increasing temperatures on the Earth. So our global temperatures have risen by about 2 degrees Fahrenheit over the past century. Here's a graphic using data from NASA. It shows a temperature anomaly. So it's the difference between the 1900 to 2000 average But if you want, just pay attention to the actual trend itself. And you can see that the absolute change is about 2 degrees Fahrenheit, and that temperatures have accelerated in the past since 1970. So of the last 20 years on record, 19 have rated as the top 20th years, going back to 1880 globally. And our average temperatures have increased from roughly 0.14 degrees Fahrenheit per decade since 1880 to about 0.32 since 1981. So temperatures are accelerating. So according to the Intergovernmental Panel on Climate Change, in their most recent report, they boldly stated it's unequivocal that human activity, mainly the burning of fossil fuels, is the primary cause of increased greenhouse gas concentrations and the observed warming trend that we recently reviewed. Now, looking forward, the IPCC also presents a series of global warming scenarios. These are driven by changes in carbon emissions or greenhouse gas emissions. And they're relative to the period of 1850 to 1900, so pre-industrial to just after industrialization started. You'll note that the y-axis is now in degrees centigrade. That's because global scale products tend to be in metric, and US specific ones tend to be in standard or imperial units. So if we look at the trends going forward, we have these blue trends here that relate to reduced greenhouse gas emissions. So therefore temperatures peak sometime in around the 2050s and then decrease a little bit by the end of the century. We have moderate emissions here in yellow, and we have high emissions resulting in higher temperatures in these 2 red categories. Currently, we're trending towards somewhere between this yellow and bottom red category. And we're looking at about 2.7 to 3 degrees above this average based on current global policies and projections. But there's a lot of wiggle room there as to where we're actually going to end up. And these changes in warming are all rooted in global technological, economic, and policy changes. And they're not definitive, but they're an illustrative range of guidance for us where we could end up based off of our total greenhouse gas emissions. Now, those warming scenarios and the warming globally results in a whole bunch of resultant climate change effects, such as more destructive storms or greater storm surge, increased flooding in some regions, or as we see on the American West, more instances of drought or drier conditions, or just dry conditions making great conditions for wildfires. So there's a lot of resultant climate change effects that are detrimental in terms of natural hazards. So that's a global overview. Let's now focus down on New Jersey's climate. And as we get into New Jersey's climate, I want to talk about what we think of as normal. So in climatology, we define a climate normal as the average of 30 years of measurements of a particular parameter like temperature or precipitation. You can do that at the annual scale, or you can do it at the monthly scale. And we use that to compare what we observe today against what we would expect to see. What's interesting, though, is that these climate normals are updated every 10 years. So we recently switched from a 1981 to 2010 climate normal to a 1991 to 2020 climate normal. And the big takeaway from this is what we consider normal in a climatological sense changes over time. So when we talk about what's normal, it's not rooted back to say what was occurring in the 1950s or earlier in the 20th century, but what's happened in the most recent 30 years. And when we look at these updates, New Jersey's temperatures have increased at about 0.7 degrees Fahrenheit, and precipitation has increased by about 1.2 inches. And if we were to break that out by month, you can see here with temperature that New Jersey's temperatures have increased for basically every month except November. It's a little weird. And that precipitation has increased in our summer months primarily, with some other small variations going on here. So just keep in mind that what's normal changes over time. All right, So we're going to focus in on temperature and heat as our first cut at climate change effects here in New Jersey. So much like the global temperatures, New Jersey's temperatures have been increasing, but at a faster rate. So now we have temperatures here in degrees Fahrenheit from the 1880s to present day. So the red represents a smoothing of the yearly average, and the yearly average is in black. And we've had about a 4 degrees increase in temperatures in New Jersey over this time period, which is about twice the global average. So the global average is about 2 degrees Fahrenheit, and New Jersey, we've seen about a 4 degree Fahrenheit increase. And out of the 20 warmest years on record here in New Jersey, 15 have occurred within the last 20 years, and 2021 was the 3rd warmest year on record. Now, those temperatures are, much like the global ones, actually accelerating. So here's a simple line fit of temperature trends from 1900 to 2020 versus 1970 to 2020. And what you can see is that over the longer term, temperatures have been increasing at about 0.32 degrees Fahrenheit per decade. But if we shorten that time to just from 1970 to present, it's about double that at 0.66 degrees Fahrenheit per decade. So it shows that our temperatures are increasing at an accelerated rate. And if we were to divide this around by season, our winter temperatures are increasing at a much faster rate than, say, our summer or fall. I believe it was about 1.5 times the rate. And looking forward with our temperatures, we had these projections from NOAA that detail the temperature change relative to a baseline here in black. The black line baseline is the average from 1901 to 1960. And the orange here represents our observations. And then the green represents our low emissions trajectory of where our temperatures could be by the end of the century. And the red represents higher emissions trajectory. So higher greenhouse gas emissions and lower greenhouse gas emissions. And what you can see is that by the end of the century, with lower emissions, we're looking at about a 3 to 9 degree Fahrenheit increase compared to this baseline. And for high emissions, about a 6 to 13 degree increase, almost up to 14 in some cases. But let's put that in some other words. By the middle of the century, projections indicate that about 70% of New Jersey summers are going to be warmer than any before 2006. And by the end of the century, about 90% of New Jersey summers will be warmer than any before 2006. And we care about those heightened temperatures for a number of reasons. One of the biggest that jumps out, though, is increased instances of heat-related illnesses, hospital admissions, or deaths amongst vulnerable populations. So as the atmosphere warms, it's able to hold a lot more water vapor. Doesn't mean it does so in every instance, but it can hold more water. And here in New Jersey, we have a humid climate. So that increased humidity actually restricts our body's ability to cool off because we cool off by perspiring. We sweat and that sweat evaporates. With higher humidity, that process doesn't work as effectively. So we have individual higher heat stress risk. Similarly, extreme heat can overburden building cooling systems. So people that are outside that are really experiencing a lot of heat stress, they may not be able to find reprieve going indoors where you would hopefully find AC. And also of interest in New Jersey is that extreme temperature effects are amplified in urban environments and suburban environments. So in like an urban environment, say like Newark, paved surfaces and a lack of vegetation can contribute to the urban heat island effect. That means that those impervious surfaces and lack of vegetation creates an area where the ambient temperatures are a bit higher than the other surrounding rural or forested areas outside of the city. And that also can happen to a lesser effect in suburban environments. And New Jersey has a lot of urban and suburban environments. So it's important to us moving forward to think about how our urban heat islands may change with climate change. In addition, our heightened temperatures can cause degraded air quality. So on hot days, more ground level ozone is produced, which is really bad for people with asthma, for example. We can increase the prevalence of certain disease-borne vectors. Certain species like mosquitoes or ticks will have an expanded range with increased temperatures. And they may introduce various diseases like Lyme disease or West Nile virus into new locations because of their expanded range. High temperatures affect our agricultural production. Crops like a certain temperature range, and there's a chance that here in New Jersey, our temperatures may be high enough that a lot of our current crops may not be viable. On the flip side, that also means that certain crops may now be viable that are maybe more traditionally southern species. In addition, we'll be seeing a longer growing season, which can be beneficial to a number of crops and harvest yields within the state. And then, as we discussed at the individual level, increased instances of heat stress emergencies. Okay, so that's an overview of heat and temperature effects in New Jersey. Now let's transition to looking at sea level rise, because that's also basically a direct consequence of increased global temperatures. So it's no shocker, sea level is rising. This is a global measurement of mean sea level, so that's MSL, in millimeters, and it's a change over time from the early mid-90s to today, effectively. And the reason why the time series starts in the early 90s is that's when we started having good satellite measurements of global sea level change. Before then, we had to rely on a smattering of global tide gauges. And you can see that sea level is accelerating over time because this curve bends upward just a bit. And since the mid-90s, we've had a swing of about 80 millimeters of sea level rise, which translates to about 3.15 inches of global mean sea level rise. And if we were to look at the rates of change over the past century, from 1900 to 2000, the rate of sea level rise was about 1.7 millimeters per year. And over this more recent time period, it's about 3.3 millimeters a year. So not only is sea level rising, but the rate at which it's rising is accelerating. And if we return back to our IPCC projections of sea level, coincident with those climate change projections, we get this graphic here. So this is now global mean sea level change relative to the year 1900. And it's, again, now in metric because it's a global scale product. And you can see that tracking where I said that we were currently going towards, that's in between this orange and this first red here, we're looking at about 3/4 of a meter of sea level rise by 2100, assuming we don't, curb our emissions dramatically or accelerate our emissions dramatically. Now, the IPCC does provide for this high impact, kind of low likelihood scenario where we don't have a good handle on ice sheet dynamics and melting rates and that kind of stuff, but it's much less likely. So I want us to focus in on this suite here as our kind of more likely scenarios with sea level change. Now, this is global sea level rise, but that's not necessarily how we experience it on land. So I want to talk to you about relative sea level rise really quickly. So if global sea level rise is this absolute change in sea level over time, relative sea level rise is the amount of sea level you experience if you're standing on the beach. Say you're standing on the beach in coastal New Jersey or near Atlantic City for 40 years, how would you experience sea level rise? And what we find is it is not consistent across the entirety of the United States. So this represents the relative change in sea level by location from the year 1960 to 2020. And this is sourced from EPA and NOAA. And what you can see is in the mid-Atlantic region here, right around us in New Jersey, our sea level over this time has increased by more than 8 inches. But that's not, like I said, consistent. If you go out to California, it's a much lower rate of relative sea level change. And in Alaska, it's actually decreasing. And there's a lot of factors that go into it. So I want to talk about what contributes to global sea level rise, regional, and then relative local sea level rise. So at the global scale, there's a few big processes. The first is melting of glaciers on land, melting of ice sheets in Greenland and Antarctica causes the meltwater to funnel directly into the ocean, and it fills up like a bathtub. So this is where I said temperatures have a direct consequence on sea level rise. As the world warms, ice melts, and that water ends up in the ocean. Also, as the ocean warms, the water in it expands just a bit. So just like heating up the air in a hot air balloon causes it to expand, or as the seasons change and the materials in your house expand and contract and cause all that creaking, the ocean itself also expands with some heat. So as the atmosphere warms, so does the ocean, and it expands a bit. But the ocean itself is on average about 4 kilometers deep, and it covers a huge swath of the ocean, of the Earth's surface. So even a small amount of expansion of ocean water causes a very noticeable effect for us at the surface. To a lesser degree, the terrestrial storage of water. So you put up a dam and store a whole bunch of water on land, or release a bunch of dams, that can affect sea level at the global and regional scale. Now, at a more regional scale, so think coastal mid-Atlantic area here in the US, there's a lot of complicated physics that go into how it experiences sea level change. But one of the big things I want to kind of clarify is the ocean surface is not flat. Even if you remove all the waves, the ocean has topography to it based on a whole bunch of different factors. So different regions will experience different sea level changes at different rates. And this can be driven by changes in ocean circulation, changes in ocean salinity in certain locations. It's a lot of complicated dynamics that I don't want to bore you with today. And then at a local level, and this is important here in New Jersey as well, is that the land itself can be rising or falling, vertical land motion. And in coastal New Jersey, our land's actually subsiding or sinking over time. So due to that combined factor of global sea level increasing and New Jersey sinking just a bit, we experience an accelerated rate of sea level rise compared to the global average. And we actually see a manifestation of that at the Atlantic City tide gauge. So this graph shows the monthly mean sea level here in black with just a linear trend at Atlantic City. So sea level here is now in inches, and it's relative to the start of the time series, which is in 1911. And we've experienced about 18 inches of sea level rise over this entire time period. And looking forward here in coastal New Jersey, we can use this graphic from Rutgers-led report for the state of New Jersey in 2019 to get a sense of where our sea levels are going to go in the future. So we now have sea level rise in feet relative to the year 2000 listed here. And this is for moderate greenhouse gas emissions. And there's a whole bunch of stuff going on here, but in short, the tan area represents the likely range of sea level rise within a given year. And the red represents kind of our median or best guess estimate of where sea level will be at a given year. So if we look at year 2100 here, it's about a 2 to 5 foot increase compared to the year 2000. And the red line here is about 3.3 feet or around a meter conveniently. But let's put that into words. So relative to the average from 1991 to the year 2000, so again, I'm sorry, 2009, so that averages out to the year 2000. Sea level is projected to increase by about half a foot to a foot by 2030, and about 1 foot to 2 feet by 2050 in New Jersey. And prior to that, it's not really dependent on emissions. We're kind of locked in for these ranges of increases, regardless of whether we increase or curb our emissions. But after 2050 is when we start to see the impact of those global greenhouse gas emissions. So for a low emissions scenario and low warming, sea level would be expected to be about 1.5 to 4 feet higher than the year 2000. And with higher emissions, it's about 2.5 to 6.5 feet higher. And when we think about the effects of sea level rise, the first thing that pops into a lot of people's head is just the oceans encroaching on land and gobbling up property. And that is an effect, but it's not the most immediate effects that we're going to see. One of the strongest and most immediate effects that we're going to see is the influence of sea level rise on the amount of damage from storm surge. So I really like this little graphic. Here we have a little house on a hill, and it's currently protected during existing high tide. So the high tide doesn't reach it. And if a storm blows in, say a nor'easter or a hurricane, the storm surge, or the vertical extent of water due to those storm effects, does not currently reach the house. You'll notice that storm surge acts just like an additive. It just stacks on top of the current sea level baseline. Now, with sea level rise, that baseline shifted up such that storm surge now acts on a higher baseline, and it can now impact the house. So with sea level rise, there's potential for storm surge to penetrate further inland and flood some areas much more deeply. And we've seen a manifestation of that already here in New Jersey with Hurricane Sandy. So here is the storm surge extent from Hurricane Sandy. And a recent study estimated that about 13% of the total property damage in New Jersey from Hurricane Sandy storm surge could be attributed to human-caused sea level rise. So that's to the tune of about $4 billion. And we can think about it as well in terms of comparing it to the past. So a coastal storm today would cause more flooding damage than the same storm would 50 years ago because sea level has shifted that baseline higher. And if we want to think about it in terms of frequency, today's 100-year intensity coastal flooding event, so that's a coastal flooding event we would expect to occur maybe about 1 in 100 years, or has, we would say, a 1% chance of occurring each year, is projected to occur 5 times as frequently by 2050. It's mainly because it doesn't take as big of a storm to generate the same amount of flooding when you have a shifted higher baseline. In addition to storm surge flooding, we also have a little bit more of an insidious type of flooding called tidal flooding. Now, tidal flooding is, as its name suggests, flooding that is due to extremely high tides, causing some level of flooding, generally a low level of flooding, without the influence of a big storm or anything of that sort. This can also be called nuisance flooding or sunny day flooding. And you can see in this image here from Mantua King that it's not heavily dramatic. There's not homes being swept away, but it's flooding homes or cutting off access to their driveways or flooding infrastructure like the road here. And tidal flooding is important because it presents a low level of flooding, but with a high frequency. So there's repeated damage or repeated flooding impacts that are happening over time. If we look at how tidal floodings have been impacting Atlantic City, and the reason why we're looking at Atlantic City is because there's a tide gauge there, as well as projections, we can see that the frequency of our tidal flooding days are going to increase. So in this graphic, on the y-axis, we have the number of days per year that the Atlantic City tide gauge registers tidal flooding. The orange here represents observation data, and then the 2 blue data sets here represent NOAA's intermediate and intermediate low sea level rise scenarios. So they kind of bound our current track of sea level rise here in coastal New Jersey. This cutout just represents only the observed data. And you can see that since the early 1900s, the number of days per year experiencing tidal flooding has increased. And if we were to look at our future projections, you can see that by 2060, about 1/3 to almost 2/3 or more of days in Atlantic City would be experiencing tidal flooding. And by the end of the century, 2/3 to virtually every day would be experiencing tidal flooding in Atlantic City. Some other interesting effects from sea level rise is the change in estuary salinity and where that salinity is located within a river. So here is the Delaware River. It flows down into the Delaware Bay, and it presents fresh water that then meets with ocean water, mixes with it in salty water or brackish water, and then becomes salt water as it meets the ocean. And that interface where it transitions from fresh to salt water is called the salt front. And it's actually a distance. It's not like a hard cutoff. It actually has a transition zone. And that zone is generally located around here. It changes based off of flow conditions of the Delaware. It changes off of certain tidal conditions and the like, but in general, it's located in this area. With sea level rise, the balance between the flow of the river and the force coming in from the ocean changes, and it pushes that saltwater front further upriver. So here's estimates of where it would be with 1 foot, 2 feet, and 3 feet of sea level rise here in red. And that presents a number of unique challenges and dangers. One, it's within striking distance of one of these drinking water intakes, so a low flow here could cause the salt front to maybe oscillate up to there. It also changes this freshwater ecosystem habitat to brackish or at least saltier water. So that impacts the animals and plants that live along that area. And parts of the Delaware work to recharge some of our aquifers in the state. And we're not 100% certain exactly which part. It's in this general area, but we're not exactly sure exactly where. And if you start recharging with salt water as opposed to fresh water, that fouls the aquifer, making it less usable for irrigation or drinking water. Sea level rise also has a noticeable impact on agriculture. We don't think about sea level rise in agriculture as much, but we have actually a good amount of coastal farmland here in New Jersey. And as we discussed, with increased storm surge capability to penetrate further inland, that means that fields could be flooded with salt water more easily, and crops do not react well to salt water or salt. So that means that we'd have decreased production after a flooding event. In response to sea levels increasing, the local water table, the local groundwater table, will often also increase in elevation. So it would become a little bit more shallow. And if it's close to the surface, that can create consistently wet soils in our croplands. And that's not good for plants. It can cause disease and root rot, and the conditions just aren't as good for the crops. And along some of these areas where there's wells for fresh water to irrigate crops, if those are close enough to a tidal waterway, the salt water pushing further up, not just the Delaware, but every estuary, every ocean or river mouth that leads into the ocean, could result in those wells now pumping salt water, which obviously impacts irrigation practices. And to underscore this, some of our co-authors looked into the effects of 1 foot of sea level rise on New Jersey agriculture. So in this image here, we have in green the flooding extent of just 1 foot of sea level rise versus qualified farm parcels or impacted ones here in blue. And this is just focusing in on Salem and Cumberland counties. But they did this analysis for the entire state and found about 16,600 acres of current agricultural land in coastal New Jersey would be impacted by 1 foot of sea level rise. And so the affected farms account for an area of about 45,000 acres with a farmland assessed value of almost 18 million. So not only does sea level rise affect the crops, but there is an underscore of the economic impact to that as well. All right, so we're going to transition now to talking about changes in precipitation within New Jersey. Pictured here is the annual average precipitation for New Jersey, average for the entire state. So it's total precipitation in inches. The green line represents the annual mean. You can see it oscillates a lot. And the black lines represent decadal means to help us get a handle on any trends that would be there. And one of the things going into this discussion of precipitation that we should keep in mind is that with higher temperatures, the atmosphere can hold more water vapor, same as we discussed with the humidity earlier. And that introduces the possibility of producing more precipitation. So it doesn't mean it has to, it just means that it can. And what we see with New Jersey is that we have very high year-to-year variability in rainfall. And that's true in most locations. But with climate change, what we've seen is that this up and down trend has become decidedly spikier and larger. Our rainfall has become more variable year to year here in New Jersey. And if you were to actually do the statistics to figure out if there is any sort of discernible trend in whether rainfall is increased or decreased, We've seen about a 7% increase in rainfall since the early 1900s here in New Jersey. And the top 5 wettest years have all occurred since 1975. Now, if we look at projected precipitation, New Jersey mean annual precipitation is projected to be about 5 to 8% higher than the 2001 to 2020 mean by the end of the century for moderate to high emissions. So the moderate is 5%, high is 8%. And we see that reflected in other climate change products. So this is also from NOAA, and it's showing projected change in spring precipitation for the contiguous US. And you can see New Jersey's highlighted here a little bit, showing about a 5 to 15% increase in rainfall amount for high emissions. Now we see the same thing in spring, in winter. We don't see as much of a change in summer or fall in our projections. What our projections are also saying, though, is that we'll have longer dry spells between individual rainfall events. And that's particularly during the summer season. So that can affect irrigation and water supply practices where our rainfall events are punctuated by longer periods of dry conditions. But where we're seeing a noticeable change is in extreme precipitation. Extreme rainfall in New Jersey is becoming more frequent and it's becoming larger. So typically, when we determine what kind of rainfall we expect to see, we use data from 1950 to the year 2000 from NOAA to figure out, okay, this is how frequently we expect a rainfall amount of 3 or 4 inches, let's say. A recent study commissioned by the State Department of Environmental Protection, led by a colleague of ours at Cornell, found that by adding 19 more years of data, so extending that data set from the year 2000 to the year 2019, found that in many cases, there's a greater than 2.5% increase in those extreme rainfall estimates by incorporating that recent data. And if we were to look at this graphic here, also from NOAA, it shows the number of days with precipitation of 2 inches or more throughout the state. So each black dot represents the average of days exceeding 2 inches or more of rainfall. And the bars here represent 5-year averages. And then the black line across represents just the entire average. And what you can see is that we've had an increase over time in our number of 2-inch precipitation events. There's still a lot of variability because rainfall is extremely variable, but we're seeing an increase. And if we look at projections for the 24-hour 100-year rainfall event, so that is the amount of rainfall you get in 24 hours that you would expect to see on average once every 100 years, or it has a 1% chance of occurring each year. If we look at that by the end of the century, projections are 2.5 to 10% greater amount of rainfall of that scale event in central and coastal New Jersey, or a 20 to 25% increase in northern New Jersey. And the big takeaway from this is we expect extreme precipitation to increase, and therefore our extreme rainfall guidance based on historical observations is still useful, but it needs to be supplemented by model projections to help account for future effects. And speaking of effects, when we look at the effects of extreme precipitation, a lot of it's pretty self-explanatory. More precipitation means that there's a higher chance of floods, they're more frequent. We have a greater loss of life and property and infrastructure damage. So for example, here is an example of like a flooded highway in New Brunswick. So this is after Hurricane Irene, but it's still an extreme rainfall scenario. And flooding also has compounding indirect effects beyond just the loss of life and property damage. Often after a flood, people are cut off, maybe trapped in their homes, or they have no power. So they'll bring their outdoor cooking equipment, their grills and stuff inside to heat homes or to cook. And that can cause carbon monoxide poisoning for a lot of individuals. You see an uptick in that after a flood generally. And also the floodwaters themselves can carry wastes, which can contaminate food and water supplies. In terms of agricultural impacts, heavy rainfall can reduce growth, and flooding can as well, delay planting, And we talked about how wetter soils can increase susceptibility to disease and root rot. Also, it's harder to get farm equipment out on wet soils because it can compact it or it can get caught in the mire. That would be the field. So I want to focus in on a particular extreme event, an extreme rainfall from last year, and that's post-tropical storm Ida. So Ida started out as a hurricane in the Gulf Coast. It made landfall in Louisiana, and after being downgraded from a hurricane, the storm persisted over land, arriving in New Jersey from the southwest on September 1st. And it brought with it tornadoes, rain, a huge amount of rainfall, and in a short amount of time, and a lot of flooding that killed 30 people and represents the second greatest loss of life from a natural disaster event only in New Jersey, only exceeded by Hurricane Sandy. And we're still figuring out the damage totals, but it's been estimated that the tally for the entirety of the US Northeast from Ida was about $16 to $24 billion worth of damage. In New Jersey proper, we had a huge amount of rainfall. We registered more than 9.2 inches of rainfall in Hillsborough and Flemington. And if we were to look at the New York weather station, we registered rainfall amounts that we would equate to a 1,000-year event, or something we'd expect to occur once every 1,000 years, has a 0.1% chance of occurring each year. This image here represents the amount of rainfall received within 6 hours across the state, and their kind of their intensity in terms of what we would expect to see that in terms of its frequency. And you can see that for large swaths of the state, we got rainfall in that period that we don't expect to see maybe once every 500 years or so, if not once every 1,000 years. And the flash flooding that Ida brought exceeded 10 to 20 times the typical threshold that meteorologists use for a warning for flash flooding. In terms of riverine flooding, there's a lot of flooding throughout the state, but the hardest hit areas were generally the Raritan River and especially at Manville in New Jersey. So this is the USGS stream gauge there. The blue line represents the elevation of the water, and the red represents its flood stage when you would consider it in a flooding stage. And you can see that it exceeded that elevation dramatically. It actually exceeded 27 feet, which resulted in a lot of flooding. You can see here, this is Raritan, New Jersey, so just upstream of Manville. But you can see that the Raritan River has exceeded its banks. It is flooding areas, homes, displacing people, and kind of just causing damage and gumming up businesses. So when we look at Ida, we want to see if we can glean any insight to how future storms may develop and what we could expect here in New Jersey. So future Atlantic tropical cyclones, we expect them to become more intense because warmer waters in the ocean fuel tropical cyclone intensity. So expect them to become more energetic, so higher winds, intensify more rapidly, so they'll jump up in category, or we'll have more rainfall. And we actually saw that with Ida, where before it made landfall, it actually hit a tongue of warm water that caused it to jump up in category and intensity before it hit. Now, for New Jersey, obviously, I've discussed it before, we're expecting more rainfall in general and a lot more intense rainfall. And we think that today's 100-year event, so our storm or our rainfall event that's frequency 1% chance of happening each year, will track more closely to the 50-year event. So it becomes about twice as frequent by the end of the century. And Ida could be a harbinger of what future storms rainfall here in New Jersey may look like. And it really underscores that New Jersey's susceptible to flooding, both coastal as well as pluvial or rainfall and riverine flooding moving forward. And I want to leave off briefly discussing how climate change interacts with vulnerable populations. And when I say vulnerability, I'm defining that as being prone to harm by climate change or less able to respond to climate shocks and stressors. So think of it in terms of income. A lower income community may have less money to adapt to climate change, or the ability or less money to recover from a climate change driven disaster compared to a wealthier community. So that's why we would classify them as vulnerable. And some people, households, and communities are more vulnerable to climate change impacts than others. And it's primarily driven by demographic and economic factors like age, health, income, and wealth. A simple example is if you think about children, they have an immature physiology. They're dependent on adults for just about everything in their lives. They are not able to adapt to extreme heat or get out of the way or find reprieve from it as easily. Similarly, older adults, as we get older, our bodies tend to lose the ability to thermoregulate as well. So older adults tend to be more vulnerable to heat exposure as well, compared to, say, a healthy 20 to 50-year-old. So this kind of underscores that there's a lot of different groups that are vulnerable to climate change, and they're impacted unequally. And climate change itself may amplify existing inequalities that we have within the state. And our socially vulnerable populations are more impacted by the same amount of hazard exposure compared to those that are more resilient. If we were to look at the geography of socially vulnerable populations in New Jersey, we have this graphic here on the left. So this is the Center for Disease Control and Prevention's Social Vulnerability Index. So yellow here is lowest vulnerability and dark blue is the highest vulnerability. And you can see that it's not equally distributed throughout the state. Some communities are less vulnerable than others. And we need to consider that geography when we consider the geography of climate change. So here on the right are the projected number of additional days above 95 degrees by 2060 compared to today for high amounts of climate change, or emissions rather. And you can see that geography can introduce more hazards to certain vulnerable populations compared to other locations where there's vulnerable populations, but the increase maybe isn't as strong. So when we consider our vulnerable populations, we have to consider not only their resources and what we can provide them, but also what kind of hazards they are most vulnerable to and what they will potentially be exposed to going forward. All right, and with that, I'd like to say thank you. I'm going to bring on now Dr. Anthony Broccoli and Dr. David Robinson to help with the Q&A portion, but I'd like to thank my co-authors of the report, as well as our reviewers, Keith Dixon at NOAA and Art DiGaetano at the Northeast Regional Climate Center. So with that, we'll take some questions. Thank you.
Thanks, James. Can you hear me okay?
Yes.
Great. Then we have Tony and Dave, you're there?
We are here.
We're
Perfect.
here.
Okay, folks, throw your questions in the chat box, but I've been moderating it and we've got a few questions, so I will just jump in. So yes, James, lots of information to take in. A question came in from someone who was hoping you could clarify the climate normals, perhaps the number of years they cover, and then how often they're updated.
Dave, I think that'd be a great question for you.
Yeah, great question. They're 30-year normals, and they're updated every 10 years. So we switched from the 1981 to 2010 normals to 1991 to 2020 normals. So essentially, we're removing the 80s and adding the teens. So when we're looking at the changes, we're really looking at the changes from the 80s decade to the teens decade, because the 90s and the aughts stayed together. And that's just a convention globally, not just prescribed by us or even by just the US National Climate Center.
Great. Thank you. Someone asks, are there significant differences in the temperature changes in the northwest of New Jersey versus the southeast of New Jersey? And could this be due to geography? So maybe that's a Dave and or Tony question.
Go ahead,
Well,
Tony.
I think I'll just start out. I think there's two parts to that question, two ways of thinking about that question. One is, will the changes be different in magnitude in those two places? The other one would be, will the resulting climate be different in those two places? So I'll just speak to the first question, and I'll say that with the current amount of detail that we can simulate with climate models, I wouldn't have a good deal of confidence that we could distinguish between the amount of climate change happening in the northwestern part and the amount happening in the southeastern part. But Dave, I'm sure you can share the big differences in climate between those parts of the state.
Yeah, I mean, we're talking in some respects in the winter about that magic mark of the freezing point. We're often above that freezing point in South Jersey during the winter, even now. But up in the Northwest, it's more common to have temperatures below freezing. And with change, that might see that tip upwards and reduce the amount of snow in the northwestern part of the state. The number of days with ice-covered ponds and lakes where you could get on it for ice fishing, perhaps. So that's what I would see as the major difference in the winter. In the summer, it's quite interesting because you've got the continental effects of being inland, but along the coast, you have the maritime impacts. And we know our oceans are warming. So we have to look to the oceans to see what's going on, especially along the coast, whereas inland, it's a little less directly connected with the oceans, although we are, we're a border state, we're a marine state. So a lot of differences across a pretty small state. And as Tony said, it's very difficult to know exactly how those changes are going to occur.
Thank you. So we had a question about any thoughts about why November has not seen similar temperature changes, as long as we're talking about temperature.
Yeah, well, that's back to the normals again. And so it basically says that in the 80s versus the teens, we didn't have much of a difference in temperature. And even precipitation went down. And the fact is, we don't know. And the other way of looking at it, it's a relatively short sample period to compare 10 years to another 10 years. So I wouldn't make a lot out of it, but it is a bit of a head scratcher. It would be an interesting project for, say, a senior project or something like that here at the university.
So go ahead, Tony, sorry.
No, I just wanted to add that I completely agree with everything that Dave just said and about the small sample, but it's even smaller, right? Because it's not really 10 years, it's 10 Novembers that come out of the average and 10 more Novembers come into the average. And there's enough variability from year to year that some of these things are going to show up just for reasons that are essentially random.
Got it. So I'm going to ask one more. I think it's a temperature related question. Oh, two more, because we have to give some time to the other impacts. But so someone's asking about temperature elevation and the impacts of developed or impervious surfaces versus forested or meadow areas. So sort of about sort of heat island and that kind of thing. So I didn't know who wants to grab that. Dave, do you want to take a shot at it?
I'll take the first shot at that, and I'm going to go right to evening time in the summers. We don't see as big a difference between urban and rural areas during the daytimes in the summer. It's more inland versus coastal, but at night, I have a figure I show in many of my talks, which looks like the population density of the state and looks at a map of temperatures late in on a summer evening, on a warm summer evening. And the greatest warmth is right where the population density is greater, where the streets and the rooftops are still holding that heat from the previous day, where the air conditioners are belching out warmth. And that's a really critical issue for environmental justice and health. It's the nighttime warming. So that would be part of my take on things, but I think an important part.
And as a follow-up to that, in terms of health, there's been a lot of studies that have linked to higher overnight temperatures leading to worse health outcomes. And so it's just exacerbated in those urban heat island areas.
Right.
So this is an interesting question we got. So the graph from Atlantic City related to flooding reminded me of graphs I've seen of Western wildfires. a big increase in impact starting around 2000. And while wildfire risk may be less in New Jersey than out west, although we do get sometimes many wildfires a year here, are you guys aware of any studies on the change in the future risk of New Jersey wildfire?
I have looked into it, but I am not aware of anyone that's actually really delved into it super deeply.
Yeah, I'm not either. And I think it's a very interesting question because, for example, in the Pine Barrens, the wildfire season is typically in the spring. As we start to get more heating from the sun, the soil starts to dry out. We often get a lot of windy days in the spring. And you could imagine that as the climate gets warmer, the transition to that dry, windy season might begin a little bit earlier and perhaps prolong the period where there could be fire risk. So I think that really would be an interesting study, but I'm not aware of anyone who's looked at it rigorously.
And I don't know if our climate models could capture that just yet.
No, but James, you did speak to the fact that in a climate changed world here in Jersey, we'll have these intense bursts of precipitation, but longer periods of dry conditions between those bursts.
Right.
And with that, the pinelands can dry out very quickly with their sandy soils and such. So that could exacerbate the fire threat in the future. These bursts of rain and protracted periods of dry weather.
Mm-hmm.
We did have a question about the current trajectory related to sea level rise and what areas of coastal New Jersey would be affected. And what I'm going to do is stick in the chat box the link to our data tools that we've been developing, because I don't know if any of you want to discuss this, but in the meantime, I'll just say that the Research Center has been developing tools to help communities and citizens see the projected impacts, and these tools are constantly being updated and expanded. And we'll actually be releasing a New Jersey HazAdapt in the next week or so, and which looks at community lifelines like energy facilities, health and medical facilities, communication facilities for the emergency management community. But the link I sent you to includes the Flood Mapper tool and also the Forest Adapt tool. And we also we'll be releasing in, I hope, the next month, probably sooner, the New Jersey Climate Dashboard. And we'll also be developing a Health Adapt, and we hope to develop an Ag Adapt. So I don't know, Tony, Dave, James, if you have anything else you want to talk about in respect to coastal community exposure.
I would have just plugged the same thing because it's a really wide swath of things to do, and it's probably better just to visualize it through a tool.
Okay.
Yeah, and the thing that I would add is, to a first approximation, the vulnerability depends on how far above sea level you are. But one of the things we learned from Hurricane Sandy is that even people who may not think that they're close to the ocean could be affected by storm surge flooding. It happened in places like Sayreville and Woodbridge, that we don't think of as being coastal locations. And that's where these tools really come in handy, because you can see what areas would be inundated by a certain amount of sea level rise.
Right. If you remember, I showed a slide. Sorry, I'm having some difficulty with it here, but I showed a slide regarding Hurricane Sandy's storm surge extent. And maybe I could just show that to kind of underscore your point, Tony. Do this one.
That's a great point for the extremes, but the question was also which ones would be first affected. And for that, I'd look at where the nuisance flooding is increasing the most, because those are the first areas day to day are going to see more of that. But then comes along the big storms, and there's your
and you can see there's significant places further inland that got flooded by storm surge. And, as Tony said, they're far away from the actual, what we consider the coastline.
So
and I mean, just as an anecdote, in the presentation, James showed that picture of Route 18 in New Brunswick being flooded from Hurricane Irene. Route 18 in New Brunswick got flooded by Hurricane Sandy also, except it wasn't water coming down the river from upstream. It was coming up the estuary from Raritan Bay.
Right.
Get you going and coming.
So we're over time, but I'll ask one last question because I have had a couple people say they would be interested in the answer to this question, and I know you guys will indulge us. So this question is, if all the independent research and independent surrogate data on temperature, sea level rise, salinity, rainfall, if the markers are so clear to demonstrate climate change, what evidence are groups using to say there isn't climate change or that it's being overstated? Is it all rhetoric without any scientific evidence, or folks just are trying to understand why folks are saying that it's less influenced by human impact? So I know that's not always a pleasant topic to discuss, but I do know you guys get that very often. So I thought I would lateral it to you because folks here are interested to hear what you have to say about that.
Well, Marge, I'm sure glad you saved the easiest question for last. No, I mean, I think that is a very good question. And I would point to a few things. First of all, I think one of the issues is that the processes that are responsible for the changing climate, primarily the emission of carbon dioxide from burning fossil fuels, that's the way we get most of our energy. And so it would be nice if we could think that it didn't have any harmful effects on us or on the planet. The analogy I sometimes use, I really wish there was a study that would come out that would say that eating cheeseburgers was good for you. And so there's not, but it would be nice if it were true. And I think in some cases, it's not the science that's the issue, it's the conclusions that the science leads to that make people uncomfortable with those studies. The other thing is that if you're sufficiently motivated, you can cherry pick certain bits of evidence. You'll pick some place and say, well, for example, we talked about it before. If global warming is happening, then why hasn't November gotten warmer in the latest normals for New Jersey than the previous ones? Okay, but other months have gotten a lot warmer. If you look at the totality of the evidence, it points in a clear direction.
Yeah, it's funny. You took cherry picking right out of my mouth. But everyone has to be careful about that. So I think it's looking at the multitude of things going on and multiple variables, not just focusing on one variable and one particular period of time. But the difficulty is that the climate system is naturally variable. It has been since the beginning of time. And so we're operating now on a higher starting plane. And every day our weather and climate is affected by anthropogenic change. But it can be very difficult to separate that out on an individual day or month or even season. But as Tony said, when you take the totality of it, you see an inescapable fact that not just, and another thing is to look beyond New Jersey as well. It's not just New Jersey. It's not just one variable. It's everywhere. But that's tough. That's tough to get your hands around.
And I would also add that a lot of times there's a fundamental misunderstanding of how science itself works. A study is published saying maybe they found like a result that they didn't see much climate change impact in one area or not. And that goes out to the broader scientific community to look at, contradict if needed. Generally in science, a single research outcome does not overturn decades of research. And a lot of times people will take that and just say, oh my goodness, and just run with it as opposed to seeing it in context.
Yeah, and I might add one other thing as well. I think as human beings, we're not really wired to notice changes that happen very slowly. We can notice changes in weather. Yesterday was beautiful, it was in the 70s, and today it's in the 50s and raining. You really do have to look at data to see evidence of a changing climate. And if you're going to say, well, gee, it was really cold last week, or we had a big snowstorm, where is global warming? you can say that, but that's not really what we're talking about. We're talking about the big picture, what's happening when you look at everything over a long period of time.
Well, thank you all for taking the time from your extremely busy schedules, especially during finals time, to speak to our citizens and residents in New Jersey. And we thank all of you for joining us today. The recording of this will be up on our website. There's much more information on our website as well. And don't be strangers. If you have questions, you're welcome to email them to us, to James or to me, and we will get you some answers. That's our job. So thanks again, and have a happy Mother's Day to all those mothers out there. And we will see you next time. Thank you.
Bye.
Bye-bye.